Now, having graphical representations of vectors is very handy, and these pictures are very intuitive. But as we get deeper into solving problems, what we're going to find is that pictures are lacking in precision. What we're going to need is a more precise way to work with vectors. And that means we need to come up with a new idea. And this ties in to the idea of using a coordinate system. So when you've got a coordinate system, what this lets you do is bring in specific numbers. We are going to take a vector and have its initial point at the origin of any coordinate system that we choose. Now, it doesn't matter if we are picking a coordinate system in 2 dimensions or if we are taking a coordinate system in 3 dimensions. The idea is that you're going to align one of the infinitely many vectors so that its initial point is at the origin of your coordinates, and there is the representation of the vector. And now, as soon as you've got coordinate systems like this, you know that the initial point is 0, 0, and then this final point, or the terminal point, has some coordinates, v1 and v2. This point here is 0, 0, 0, and this final point is v1, v2, v3. What we are going to do is call this a position vector because the initial point will always be at the origin. And then we are going to define what are called the components of a vector. The components of the vector are essentially the coordinates of the terminal point when we put the vector as a position vector. We will say v, we're going to put this pointy set of brackets and say v1, v2, or v is v1, v2, v3. And those numbers there are what are called the components of the vector. Now remember, it doesn't matter which of the infinitely many vectors that we choose. So for other locations, we need to determine how to figure out the components. These numbers here are essentially there to convey information about how to move, right? How do I go from the initial point to the final point? Those numbers should tell you the same bits of information regardless of where you start. So there's a simple fix. If I have a vector that starts at, let's say, x1, y1 and ends at x2 and y2, if I had placed this vector as a position vector, what it's going to tell me is that I need to move this way v1 and I need to move this way an amount v2. So the same result has to end up occurring here. Regardless of where I place the vector, it has to give me a v1 and a v2. So we are going to determine the components of the vector by a very simple subtraction. We're just going to subtract the x coordinates and the y coordinates. Now, similarly, in R3, you could do the same thing for all the different values of the terminal and initial points. So it becomes very straightforward. Now, as an example here, I have a vector. Let's say v is 1 and 2. That tells me I need to go over 1 unit and up 1 unit. So there's v. This vector is starting here. So I need to go over 1 unit and up 2 units. And in this particular case, that means I'm at 3, 2, and that this means I'm at 4 and 4. So the vector could also be represented by subtracting the x components and subtracting the y components. And it gets me to the same result at the end of the day. In this course, we are going to be using these pointed brackets, but in a lot of other places, people don't make as much of a distinction about the fact that the terminal point of a vector is equal to just the coordinates of that point. So you'll see it's much less formal in other places. Now, because we have a vector in 2D, its components are related to the terminal point, we will say that vectors in 2D live in R2, and vectors in 3D live in R3. Now, when we talk about components of a vector, we can compute lengths. To calculate length, all we're going to do is rely upon geometry. So, for example, if I have this vector again, 1 and 2, that means I'm going over 1 unit this way and 2 units that way. The length of this vector should be found from the Pythagorean theorem. And the length is equal to the hypotenuse here. And the length of the vector squared should be this bottom length, which is a 1 squared, plus this top length, which is a 2 squared. And that means I'm going to get a 5. The length, I would take the square root of both sides. And remember that since lengths are only positive, greater than or equal to 0, we will reject the negative root and say that the length of the vector is root 5. Now, generally, if I have a vector and I know its components, let's say in R3, V1, V2, V3, I could repeat the same process and use Pythagorean theorem and repeat what I did for the distance formula. The length of the vector is simply going to be the sum of the components squared, which was essentially the process that I did above. This vector has components v1 is 1, v2 is 2, and this was v1 squared plus v2 squared. As an example, let's say I'm talking about point A, which has coordinates 4, 0, negative 2. And let's say I'm talking about point B, which has coordinates 4, 2, and 1. There's a vector that goes from A to B. And if I wanted to calculate the components of the vector, I would take the terminal minus initial for all of the entries. Now remember, when you've got negatives, you need to be a little bit careful. This is going to give me a 0, 2, and a 3. The length of this vector is essentially just 0 squared plus 2 squared plus 3 squared, which is going to be the square root of 13. So how do we compute scaling and addition with components? So if I said U is a vector U1, U2, and V is a vector V1 and V2, both of these vectors live in R2. And if I wanted to visualize this, I could think of the vector U as ending at some point U1 and U2. And that means if I were to drop this value down, it would be a U1, and this over here would be a U2. And if I wanted to add another vector to it, I could use the tip to tail rule. So this would end up being the vector V, and by its component definition, this has to be V2, this has to be V1. So if I were to say, okay, the final result is this vector U plus V, it extends down to U1 plus V1, and then it extends up here to U2 plus V2. And so this leads us nicely to a definition here that U plus V, all we do to compute it is simply add the corresponding entries of the components. And this works for vectors in R3 as well. So if I wanted to talk about scaling, and I'll just illustrate this with a picture in R2. If I've got scaling, there's a vector U, and it has components U1 and U2. And if I were to take a vector that's some multiple of it, let's say CU, and for the moment, let's just assume that C is positive just in this picture, but what I end up showing you will be true regardless. I don't know what the components of this thing are. Well, the nice thing about this is that you can leverage geometry results that you already know. If I have this picture here, I could say that the length here is the length of u, whereas the length here is the length of CU, and that's from there all the way down to the bottom. I know that this has to be a height of U2, this has to be U1, this right here is a Y, and the whole base is an X. The sine of theta is opposite over hypotenuse, so it would be U2 over the length of U, but these two triangles are similar triangles, and that means it would have to be exactly the same as y over the length of CU. And that means y is equal to the length of CU times U2 over the length of U. But I already know that the length of CU is equal to C times the length of U, because remember, we're assuming C is positive. So that means its absolute value will just be itself over the length of U. And what ends up happening is I get y is CU2. And sorry, that should not be a vector, nor should this be a vector. Now, similarly, if I wanted to talk about the cosine of theta, it would be U1 over the length of U, and that could also be x over the length of CU. And if I repeat the same argument, I would find that x has to be CU1. If I talk about scaling, all that ends up happening is I scale the individual components of the vector, regardless of whether I'm in R2 or R3. And that's a nice property that ends up happening. So for example, if I were to talk about 2u minus 3v, where u is equal to -1, 2, and 0, and v is equal to 2, 3, and 4, that means 2u is just going to be every entry of u multiplied by positive 2, so it'll be -2, 4, and 0. 3v is just going to be 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. And if I wanted 2u minus 3v, it's effectively just subtraction of those components. So it would be 2 minus 6, 4 minus 9, 0 minus 12. That produces a -8, a -5, and a -12. Now, from the definition of addition and scaling, I can come up with some very useful properties. So if I have two vectors, it doesn't matter the order in which I add them. And if I have the vector A and then to it I add the vector B, there's the resultant vector, A plus B. If I had gone B and then A, I end up getting to the same result. I'm going to state the other ones, but you could also just visualize them or use the component definitions to see that they will all end up being true. If you've got more than one vector, it doesn't matter the order in which you choose to add them. A nice property is that if you add the 0 vector to any vector, you should just get back that vector to itself. We've already discussed that there is this reversal of direction. If you take a vector and reverse its direction, you'll just get the 0 vector. And remember, we'll represent the 0 vector by a single dot in space. There are several properties related to scaling. So for example, if you wanted to add two vectors first and then multiply them by a scalar, you'll get exactly the same result if you were to have scaled them first and then added them. The order in which you do it is irrelevant. You could add two scaling factors and then scale the vector, or just individually scale them and then add the results. Same thing happens if you choose to multiply or scale a result afterward. These are all relatively straightforward. There exists some scalar that if I were to put it in the front, I should just get back the vector itself. Now again, all of these properties are boring, they're seemingly obvious, but they're essential. Technically speaking, in mathematics, these properties are what define a vector. Any object that satisfies these rules gets to be called a vector. So the arrows that we've chosen or the components in the pointed brackets that we've chosen all end up satisfying these. That's why they're vectors. But there are many other things in math that are vectors as well that don't have to be arrows or components. For any vector, we can use these properties and do the following. So for example, if I give you a vector in R3, I could think of this as 3 separate vectors being added together. These 3 vectors, where v1, v2, and v3, they're all just constants. I could also think of these as being scaled. So if I wanted to, I could take out each of those scaling factors. And you could see for yourself that the result I get works out to be this. We're going to give this a special name. This vector, 1, 0, 0, we're going to call I hat. This vector we're going to call j hat, 0, 1, 0. And this vector we're going to call k hat. Any vector can be written, or we say decomposed, into an I hat, a j hat, and a k hat. These 3 vectors are called the standard basis vectors. All vectors can be written in terms of the standard basis vectors. The length of I is 1 squared plus 0 squared plus 0 squared is 1. This is what's called a unit length vector. Any vector with length 1 is called unit length. The length of j is also equal to the length of k is equal to 1, but these vectors are not equal. If you wanted to visualize them in terms of Cartesian axes, these vectors are just the unit length vectors that go in each of these directions. They clearly have the same length but different directions. These are fundamental tools in helping us go forward in this course.